Now we talked about the attention mechanism. Let's take an example. Let's look at the translation from English to French that we had before. At the time step 1 of the output sequence. So this is time step 1 of the output sequence. We can see that the decoder can rely based on the input sequence they are in order to generate U. Then in the next time step, at time step 2, mainly it should just look at watching in order to generate regard, and eventually it can based on the period in the input sequence in order to generate a period in the output sequence. So it looks like the decoder has different attentions at different time steps in the input sequence. And this is the source of the attention mechanism. As we can see in the figure, the attention mechanism is based on the encoder-decoder model. On the left side you have the encoder, and on the right side you have the decoder. We have the context variable, which is the weighted sum of the hidden states of the time steps in the encoder. So as you can see, it takes the hidden state from the encoder side, from the hidden steps from the encoder. So let's say time step t prime. This is time step t prime. The context variable of the encoder at time step t prime is the weighted average of the hidden states, all hidden states of the encoder, as we can see here. So let's say this is h t, the hidden state at time step t, h t plus 1 and h t minus 1. Then the context variable which is c t prime, which is here, is the weighted average of all the hidden states of the encoder from 1 to t, from 1 to uppercase t of the hidden states. And alpha t prime t, or the width that can be controlled so that different portions of the input sequence can be focused on at different time steps and encoded into the context variable of the corresponding time step. So they are applied here and there and there. Given the time step t prime of the output sequence, the width alpha t prime t at different time step t is a probability distribution in which we use a Somix function. This is happening here. Here I rewrite t prime because we are now in a new slide. T prime, that is a t prime time step in the output sequence, and this is the t times ft in the input sequence, and this is t minus 1, and that is t plus 1. Then correspondingly, we have the width alpha, t prime t, and this is alpha t prime t plus 1, and the previous one is alpha t prime t minus 1. Looking at the Somix function, the term e t prime t, which is the input to the Somix function. So we have e t prime t, e t prime t plus 1, and e t prime t minus 1. We could see that e t prime t depends on the encoder times step t prime and the encoder times step t. It is a function a of the hidden state at time step t, which is here. And the hidden state at time step t prime minus 1 from the decoder side, which is this one. Right? Because this is time step t prime minus 1. And the hidden state, yeah, I should draw the arrow the other way. So this is a hidden state s t prime minus 1. We use s for the hidden states in the decoder, and h for the encoder. One of the choices for the function a is the inner product of the vector s and the vector h if they are of the same length. In the original paper, the author actually used a tank function. The hidden state of the decoder and the hidden state of the encoder contribute to the output of the function via some weights. How can we update the hidden states? Let's use a gated recurrent unit or GU as an example. This is what we get from the equations of RGU. The hidden state at the current time step t prime at the output sequence get some contribution from the previous time step hidden state, and how much of it would be decided by the gate. The update gate z at time t prime would decide that, and this is a candidate hidden state at time step t prime, and how much of it would contribute decided by 1 minus the value of the gate, the update gate. Here I bring up the equations of the gated recurrent unit. So you can keep a look when you reading this page. We could see a lot of similarity between the two. The input previously ht, but now is yt prime minus 1, which is the output from the previous time step in the output sequence. And instead of the hidden state at time step t minus 1, now we have something similar, which is the hidden state at time t prime minus 1. And ct prime is the context variable at time t prime. And the contribution of it would be via some width, and the rest would be very much similar, the bias vector. So we can see uh, the elements in the gate, the reset gate, the update gate have the same structure. Okay, we have the same structure there. And eventually the candidate hidden state at time step t prime in the output sequence also is a time function, right, compared to here and there, a time function. Instead of ht, now you have the input from the previous time step, which is actually the output from that time step yt minus 1. The reset gate control what you get from the contribution from the previous time step t minus 1, and c prime ct prime is the context variable, and the weight, this weight control ct contribute to the current state via some width, and then the bias vector. So we see so the equations are very much similar. And with that, you can see in the example as well. At time step, let's say t prime, you have the contribution from c at t prime. You get the hidden state, this one, from the previous time step, which is s t prime minus 1. The input is from the output of the previous time step, and this is y t prime minus 1.